So now we're going to jump ahead a little bit and talk about these models and some of the other components that I think oftentimes people have either dealt with in the past or maybe they've heard of them before. And so we'll just kind of at a high level, and then we'll keep it at a high level, and then we'll start to jump down into some of the details with security models. So what I'm about to get into is a discussion of things that you probably have never heard of before, unless you have taken some theory in cybersecurity or different types of access control. So specifically when we get into this, this will be either things that maybe you've learned a long time ago and you forgot, or it'll be brand new material. So let's go ahead and jump right in. There is something that can be said about leaning into different stages of what we typically will call the secure design. And by having a secure design of a system, usually what we can do is we have a few different keywords that we need to cover before we can have a discussion on it. And those keywords start right here. So we have a subject, which is just another name for a user or process. There's an object, which is a resource that the subject uses. A closed system, an open system, and there is a difference between these two, the closed system and an open system, right? With the closed system, the industrial standards are usually WAC, and that typically allows the bad guys to customize their payloads for attacking. Whereas an open system allows for applying industrial standards to it, and thus it gives it not only a broader attack area, but a lot of times many of those issues have been mitigated with an open system. In addition to that, there's a few other concepts that we need to enumerate through. There's this word that's called, no worries. There's this word that's called confinement. And I think, in secure design, this means that specific memory is read from or written to. That means that it's confined, that process is confined to it. Bounds are basically the limits, the upper and lower bounds of any type of stack or memory address. So when we talk about like secure architecture, for instance, the resources that process that can typically be associated with the boundaries of that. And then, how we isolate things in our operating system typically allows it to either play in a sandbox environment, or it can access and go outside of that sandbox into other components. And so as a security engineer, we would want to know as much as we can about what those secure design principles are. And why do I say that? Well, not only for the purposes of your exam, but in practice, as you go back and once you become a CISSP, you get into starting to practice what you preach, and really it comes down to how can we control. We've already talked about the various types of controls, right? The technical, the administrative, and the management, as well as operational. But we can prevent, we can detect, we can correct. But it's really broken down into a few different categories of access control. And we're going to talk about these more specifically when we get into identity and access management. But at a high level, mandatory access control, discretionary access control, non-discretionary access control, rule-based, and role-based. And so when we jump into these at a later time, there will be questions on your exam that will test your knowledge with these different types of access control. So again, going back, subjects and objects, closed systems and open systems, confinement, bounds, and isolation. So one of the more difficult components to understand, because it's more abstract, are these security models. And as we go in and start to talk about this, you're going to be tested on your understanding of these different types of models. And so one of the reasons why I said before is to not get wrapped around the axle with a few, let me put the timer down on that, a few different categories of information that we've seen, is because there's so much other stuff that the 10 miles wide and an inch deep can put you in a position to really get overwhelmed. And it's more about understanding a little bit about a lot of information. And so at a high level, we're going to enumerate each of the following of these models right now. So sit back and see if you can follow along with me. So the first one is the trusted computing base. And this trusted computing base came to life with what was called the Trusted Computer System Evaluation Criteria. That's a mouthful, TCSEC. And a long time ago, I was a young whippersnapper around that time. Specifically, this TCB was from what was called the Orange Book. And the history of it really comes into play whenever you look at the series of these books that were published for the DoD standard 5200.28 for the TCSEC, because it was actually called the Rainbow Series. And that Rainbow Series was for that standard, that 5200.28, was actually a series of books that, or journals or pamphlets that were bound, that really provided you guidance. The blue book for one thing, the red book was for another, the yellow was for another one. The orange book was for how to develop a trusted computing base. And so there's two key components that come from that, not just the Rainbow Series, but specifically from the Orange Book I'm talking about. One of them is the security perimeter, and then the other one is the reference monitors. And so when we talk about a trusted computing base, really at a super high level, it is important to be one of the baseline components whenever you're building out a system. And so this next slide will probably look familiar to people that build out a network topology diagram for your RMF package. So if you're in RMF and you're doing things with RMF, some of the things that are interesting could be what's controlled inside of your boundary. So what are you responsible to, or what are you responsible for inside of your boundary? And so everything you see here is what in the TCB, the Trusted Computing Base, is called the computing system. Anything in the red here is called the untrusted computing base. Anything in the green is a security perimeter. Okay, so we have the trusted computing base is something that we can rely on, and we know everything that's going on within that operating system. And because of that, the white line here is what we typically will refer to as the security perimeter. And so this TCB allows us to confine and trap everything within it. And so immediately I think about a lot of the weapon systems that we typically will do things for, and specifically the RTOS, the real-time operating systems, that allow you to really shape that specific function of that thing to do whatever it does very, very well. And in order to be able to control that, you can confine everything inside of that security perimeter until you can't. And once you can't, then you have to open up that security perimeter to allow other systems to be able to talk to it. And so for the DoD side of the house, you may know a little bit about this, but if you don't, then that's fine. Anytime that, let's say you have something that that flies, or something that shoots, or something that seeks and destroys, it would be contained in that trusted computing base, everything that it needs to do to make its magic happen. So it would know exactly what hardware, it would know what software, it knows what controls it has. It makes sure that only the right people have the access to it, and that it enforces any type of group policy that may get pushed down to it. And that would be obviously in a Windows system. But the security policy that's enforced, even in a Linux environment, we can set up rules to make things happen, right, for security, and lock it down. So anything that needs to connect to it from the outside, like let's say we need comms to it over VSAT or Link 16, or if it's in a tactical environment, maybe a directional antenna or something like that, we would need to create what is called a trusted path. And that trusted path typically would have to go through this thing that's called the reference monitor. And so usually the way that I remember this, or the way that I usually would teach this, is like this right here. So the reference monitor is oftentimes, at least the way that I remember this, like the traffic cop or police officer, right? And so what that person's doing is sitting there directing traffic and says yes or no to whether or not you can actually come through, give you the green light to go through the directing traffic coming through, go this way, nope, you can't come in here. And so the reference monitor does just that. It's like the traffic cop for that specific TCB that allows these untrusted computers to be trusted. Typically, what this traffic cop does is it makes these different trusted, in order to be a trusted path, you typically will have to do either ICD or maybe an IDA, right? So each one of these would have to have its own ICD or IDA, which is an interface control document or an interface definition agreement that tells the traffic cop, yo, this is how we're getting ready to use your system. This is why we think we need access to your system. Or maybe it's the other way. The trusted computing base needs access to the external peripherals for one reason or another. Again, it could be attaching to radar, some sort of comms, whether it's radio or 5G. Really, the sky's the limit. If there's a little add-on widget that you need to pop on to that trusted computing base, then how do these things interact? And what does those interfaces look like? Is it over serial? Is it over HDMI? Is it over just the simple input output? So really, it becomes a way that each one of these untrusted systems become part of that trusted computing base and allows it to build that relationship. And so at a high level, this is what a trusted computing base is. To kind of bring this all together for the security models, we started the combo off with the TCSEC. Remember I mentioned about the different series of books. There's a whole ton of them. Good late night reading for if you want to fall asleep. But this one, the Trusted Computing, is the orange book. And it has different categories of ways that things are protected. It's A, B, C, and D. So check it out, because we're about to go over something else that's very similar to this. Minimal protection means it's held together with bubble gum and duct tape, so it really has no access control. Discretionary access control, which is based off of the user's discretion. So if you own an object, so if you're a subject, which is a user, and you own an object, so let's say you create a Word file, a Word document. It's at your discretion who can have access to that. Okay, so that's the type C here. Then you move up here to the B and A that gets into what's called the mandatory access control. And all of these are controlled by the system. So mandatory access control is owned and controlled by the system. Sorry for my handwriting there. Whereas the C's here, the discretionary protection and controlled access protection, are both discretionary access control. And these are controlled by the users. Okay, so discretionary access control is users, system controls it, it's mandatory access control. And we're going to jump into that probably tomorrow when we get into talking about identification or identity access control and the like. And that's going to be a great conversation. So this is the TCSEC right here. Remember, trusted computing base. That's how we do that. So another thing that you may have heard of before is this called the common criteria. The common criteria is used to define what level of testing has the secure systems been through. I was up in Camp Atterbury, and we had a prototype that we were doing some things with up there, and I remember the colonel who was evaluating our product. He came and wanted to see what was going on, and asked me, "What's the EAL level of your product?" And so with the common criteria, there's 7 different levels that are associated with it. There's the enterprise assurance level, or the evaluation assurance level of 1, which means that it's been functionally tested. To me, what this means is that it's bubblegum and duct tape that's keeping this thing together. So essentially, if somebody's got an EAL level 1 and they're professing that, it's likely they have very little testing that has done or gone on with their system. Structurally tested gets into moderate and independent level security, but it's not ready for prime time yet, right? It's not it's not readily available for the development of platforms to build upon, but it's getting there. EAL level of 3 is typically the first one that's typically accepted by the government, because it typically shows that you've had a moderate level, and it's been through that thing that you remember seeing the first night on your homework. It's coming back full circle now. The toe, right? We're not talking about nail clippings here. We're talking about the target of evaluation. And so whatever system that is that's being evaluated is the toe, right? So if the system's being evaluated, that is, quote unquote, the target of evaluation. And so because that target evaluation, it achieves these different EAL levels depending on how much rigor has been put into it. And so as we move up the food chain, right, 1 sucks, 7 is awesome, and then somewhere in between, it adds additional value to the level of effort that has been put into the testing of it. So look at this: methodically designed, tested, and reviewed is EAL level 4. Semi-formally designed and tested. Semi-formally verified, designed, and tested. And then formally verified, designed, and tested. Now, for your purposes here, you're like, yo, this is a whole bunch of stuff, Ben. What do I need to know for the exam? So for the common criteria, on your exam, the CC, right, you will have one question. And typically, it's on one of these 7 EAL level. It's in the game. So these EAL levels are they will be on the exam for one question. So yes, you have to know these. Usually it's somewhere, it's either EAL level 4 or EAL level 5. All right, last but certainly not least, the CNA process, not to be confused with CYA, but the C and A process is the certification and accreditation. So certification, you may be familiar with, but if not, then we'll go ahead and just kind of enumerate that real quick. The technical evaluation of components in its system. And in order for us to do that, we have to show that we've had testing that's been done. So like a functional quality test on FQT, maybe a test readiness review, all the way to an operational readiness review. And so the certification usually shows that everything has been tested, system, the software, the hardware, and it has controls put in place. Whereas the accreditation here is the formal approval of a system by a designated approving authority. Here's something that anybody in the DoD may have heard of before, an AO or a SCA. So the accreditation comes from the AO or the SCA. If you've not been a part of that before, this is the certification and accreditation. Typically, it's linked to the ATO, the authority to operate.